Previously, we looked at geometric series that we could actually find the sum. And I said that was one of the rare instances where you could actually write the limit of the partial sums. There is another type of series where we could do that, and that is what are called telescoping series. And they're just a special type of series. They all have a very similar look to them. Here's an example. Natural log of n plus 1 minus natural log of n from 1 to infinity. And all I want to do is write out some partial sums, and you'll quickly see why these things are called telescoping. So what do we have here? When n is 1, it's natural log of 2 minus natural log of 1. That's the first term. The next term would be natural log of 3 minus natural log of 2. The next one, natural log of 4 minus natural log of 3, and so on. And as we start to write the partial sums, we'll see that something nice is happening here, and we might already be seeing it in that expression. So remember, our notation for partial sums is s with a subscript. So s means add up just the first, s sub 1 means add up just the first term, natural log of 2 minus natural log of 1. That's just the first term. S sub 2 means add up the first two terms, so that one and that one. But we see that we've got a natural log of 2 minus a natural log of 2. Those will go away. And we'll just have the natural log of 3 minus 1, minus natural log of 1. Same thing's going to happen for the third partial sum. When we bring that in, the natural log of 2 cancels the natural log of 2. Now the natural log of 3 cancels the natural log of 3. And all we have is the natural log of 4. So no matter how high we're going up in those partial sums, all the middle terms are canceling, except for half of this first term. That natural log of 1 is always there. And then we're always left with the beginning of the next term. So we can see the pattern there that if we kept going, the kth partial sum would be natural log of, well, look at the pattern. That number is 1 bigger each time, right? Always 1 bigger than the index. So it's natural log of k plus 1. And then minus natural log of 1. So we're able to write a nice closed form expression for the partial sums here. That's the nice thing about the telescoping. And remember, by definition, a series will converge if this partial sum, if its limit converges, and diverges if the limit of these partial sums diverge. So all we have to do is take that limit. So the limit as k goes to infinity of natural log k plus 1 minus natural log of 1. Well, natural log of 1 is 0. So really, we're just looking at the limit as k goes to infinity, natural log of k plus 1. And remember, natural log grows very, very slow, but it does grow without bound. So we know this limit is infinity. So that is telling us that the series diverges. And so all we'll say then is, so the series, natural log of n plus 1 minus natural log of n, diverges, and it's not by any theorem or anything, that's by the definition, right? That's what we defined divergence to mean. Partial sum, take the limit if that limit doesn't exist, and this is a type of not existing, right? Going to infinity, it's not going to any number. So that tells us by the definition of divergence that that's a divergent series. So a couple of things about this. First of all, one of the misconceptions is that, well, if it's telescoping, it must converge because everything's just canceling off, right? So how come the sum isn't just natural log of 1, right? The natural log of 1 doesn't cancel, but everything after that cancels. It's because at any partial sum along the way, you still have that natural log piece, right? It doesn't cancel off till the next term, but when it cancels off, a new one comes in. So even though everything is canceling, there's always that bit left, which we're seeing here, and that thing is getting larger and larger and larger without bound. So in this case, the telescoping series diverged. It could have converged if this limit existed, but don't assume automatically that it's going to converge. As you can see here, it clearly doesn't always happen that a telescoping will converge. Now, another point too is, how are you going to spot this? If you were just given a series, how do you recognize that as telescoping? Well, in order for stuff to cancel, part of the second term must be in the first term, and part of the third term must be in the second term. And the way that happens is because these two are the exact same function, just shifted by 1 in our index, right? So when I increase n by 1, this becomes n plus 1, and that's n plus 2. So that n plus 1 that was in the first one is now in the next. So you're going to recognize a telescoping as having some sort of form of some function minus that exact same function, but just off by an index. So look for that. Look for a series that's defined as a difference, and the things being subtracted are exactly the same function, just shifted by an index of 1. Then you're going to get this canceling. As far as what I'd like to see from you when you make this argument is this right here. Now, whatever it takes for you to figure out that partial sum formula, I don't care. I like to write out a few terms, then write out a few partial sums to make sure I'm clear on what's happening. But however much work it takes you, I'm not concerned with that. The key thing is that you find this one way or another. So I need to see that you actually got the right formula for your partial sums. And then I want to see you take the limit. And then I want you to make your conclusion. And your conclusion is by definition. I see a lot of people say by the telescoping series theorem or something. There is no theorem being used here, right? It's just, that's the definition of divergence. So that I need your conclusion there just by definition. So this is really the end of series that we know how to find the partial sums for. Really, it's just geometric, which once we did that once, we never did it again. We just said, oh, notice that it all depends on the r. Here with telescoping, we can write the partial sums. For all series from now on, we're going to have to use some sort of theorem or property of series to determine if it's convergent or divergent. And we won't know what the sum is. We'll just know whether there is one or not.